Thank you, Leah. I love when the introduction before I start talking is, hopefully it won't be too boring. It just sets the bar just right for me. Thank you all for coming. It is really exciting to have all of you here. This is sort of a bit of an experiment for us, so it's awesome that you guys all enthusiastically responded and showed up. Really appreciate that. As Leah said, I'm Steve Marx. I'm one of the developer advocates here at Dropbox. This is me. That's not a photo. I drew that myself, actually. But the likeness is really uncanny, I think. So my name's Steve Marx. I go by Smarks. If you're trying to find me online, I'm at smarks.com, or I'm at Smarks on Twitter, or I'm github.com/Smarks, or service that hasn't been invented yet.com/Smarks. And I just kind of wanted to ease us into things. So Guido is going to get up later and talk in some detail about our new data store API and how like conflicts work in that API. And it's very interesting. And I kind of want to lead us there by telling you just a little bit about what data stores are about and why we at Dropbox think they're important and why we build them. So I've got a couple slides to show you, and then a cross your fingers style demo that's going to be live over Wi-Fi. So look forward to that. So this is kind of vaguely the Dropbox platform vision, is we want to be the file system for the internet. Like all vision statements, it's sufficiently vague that whatever we decide to do falls under it. But it's also kind of directionally correct. Like there's this gap where we've gone from single computers to this whole network thing where we have phones and tablets and computers and amazingly other people who we want to work with. And there's no sort of shared system where we can store all the data and share that with people. And that's kind of what Dropbox wants to be. So we want to be the file system for the internet. We want to be in every app. We want to be the back-end data store for your app. And we started with very much a file-centric view. So if you use Dropbox, you know how it works. You put a file in a folder, and then that file shows up on your other computers, and on the web, and on your phone, and your tablet. But files actually aren't everything. Certainly not anymore, even if they ever were. So the trouble with files is that they're monolithic and they're opaque. So a file is essentially a name and then a bunch of bytes. And to Dropbox, that's about as much as we know about a file. And really to anybody except somebody who's consuming the file, that's kind of what you know. It's monolithic, there's lots of stuff in there, and it's opaque. You don't actually get to know kind of the structure of that data. You just see that sort of bag of bytes. And this leads to a couple challenges, particularly around syncing data across device, or syncing data in general. And so monolithic means it's inefficient to sync files. It's actually really hard to figure out what part of the file changed and if that part can be synchronized just by itself. Dropbox does all sorts of magic that I don't understand that starts with kind of rsync and then goes to customizations we've made to rsync and gets well beyond my understanding of how we actually sort of efficiently communicate these sorts of changes. You can go learn how to do that and you can make some of these things more efficient, but you can't get away from the fact that the file is really a lot of different things with a lot of structure, but that structure isn't exposed. That's sort of this hidden structure. And that has to do with them being opaque. And the real problem with being opaque is that there's nothing you can really do when conflicts arise. So if I'm working on my PowerPoint deck for this presentation, and then I go offline and I go to another computer and I make a change, and then I come back and I make a different change, when all that syncing happens, there are now like two versions of the file. There's the one I edited on my laptop and the one I edited on my desktop. And Dropbox can't, and nor can anyone, figure out what should happen when there are two versions of that file. If you happen to know a lot about PowerPoint files, maybe you could figure out, oh, that what really changed was like one slide was added here and a different slide was added over here. Maybe you could do something, but you have to really know, you'd have to break this sort of opaqueness, and you have to get inside the file and really understand it. And so we can't do that as sort of a general purpose file syncing engine. And so we can't give that to developers as sort of a useful thing. The best we can give to developers on files is if two changes happen independently, they'll collide on the server and you'll end up with just two versions of the file, and we'll have this conflict. And so conflicts are really the problem out of which data stores were born. So we have this thing called the Data Store API. How many people have heard, before they saw this meetup, had heard of the Data Store API? Oh wow, that's actually a lot of you. I'm impressed, because it's sort of our newest thing. The Data Store API came out of beta in August, September? I think September, yeah. And so it's fairly new for us, and it's the first time Dropbox has really gone beyond files. And so what we did with the Data Store API is said, what if we could see all that structure, and instead of these opaque, monolithic blobs of files, we could actually see the structure of the data. We could see tables, and we could see records and fields. Then we could do a much better job of syncing. We could make it more efficient. We could automatically handle merge conflicts. And we could sort of put all this together. And so that's what we did. We built the Data Store API. It's this cross-device data syncing with automatic conflict resolution. And let's just do a demo and see what it looks like. So this is the cross your fingers part, all right, guys? I have an app here open. Let's minimize this and that. All right. I have an app open in 2 different browsers and in the iOS simulator and the Android emulator. I basically said, like, how can I guarantee that my demo will somehow break? And so I threw in all the variables, and then we're on Wi-Fi. And even worse, at some point during this demo, I'm going to turn off my Wi-Fi to show you sort of the offline stuff and turn it back on. So I'm doing everything I can to make it break, and that's my disclaimer. So I'm going to log in. The login demo there was sort of bad because it just flashed. The idea with the Data Store API is that the first thing you do is kind of get the user to authorize your app and kind of give you access to their data store. I've already authorized this app before, so just sort of give me the shortcut auto redirect thing here. So all of these are using the same data store account, and that means when I do something, by the way, this game is, I am particularly proud of this game, and very sad that I built it on company time and can't go sell this. This game is called Click the Box, and you click on the box. And that advances you to level 2. The trick is that level 2 is considerably more difficult. So I'm going to click the box. And now I'm on level 2. Oh no, wait, look. This is the demo's failing for me. Wait, I'm going to reopen this one. I think I logged out and logged back in, but didn't actually log in over here. Let's try it again. Let's see if this actually works. Okay, there we go. So at each level, I advance to the next level, and the game sort of quadruples in difficulty, I guess. The dimensions are cut by half in both, so it's a fourth the size. It gets really challenging at level 10. All right, I built in a reset. Anyway, the point is, I can play this game on my phone or my tablet or in the browser, and all this stuff is kind of syncing up. It's atypical for me to sit with my laptop and my phone at the same time and do this. What's more likely is I'm playing this game at work. Why not? And then on the way home, I play it during my commute. I actually walk like 5 minutes, so that doesn't work either. And that's kind of the scenario. So what's really interesting is what happens when I'm like offline while these things happen. And so here, let's go crazy and turn the Wi-Fi off. And I'm going to play this game. Okay, now no syncing because the Wi-Fi's off. This is a real demo. This is the proof. So I'm going to get to level 3 here, and then I pick up my device here and get to level 4. And let's say I'm really good at tapping on iOS, and here I couldn't even do it. All right, so I've done all that, and now here's an interesting question for you because we're talking about conflicts, right? What should happen when all these devices get turned on again? So I'm going to turn the Wi-Fi back on. And they're all going to connect to the server, and they're all going to send, one of them is going to say, hey, I've made it to level 3, and the other one's going to say, I've made it to level 4, and I've made it to level 6. So I'll tell you what should happen. What would you like the result to be after these kind of go all online? Recognize that this is a conflict. They all have different answers. What is the right answer here? Level 6, that's right. This is another good answer. So Ray here says it should provide you different snapshots and let you choose. This is a man who has worked with conflicts before. This is a very interesting point. Like, this is not what we decided to do, but it's a very valid answer. Like, that is a correct answer also. The answer I was looking for is it should say level 6 because that's the highest one, right? And that happens to be in this app what we want the outcome to be, I think, right? That's how. It's a level. Whichever level I've unlocked, that should be that one. It's reasonable to also say, well, it turns out this is application specific, which it is, And some apps may want to look at these things and make a decision based on some other reasoning. Like, I actually always prefer the answer from an iOS device, because I'm an Apple fan. Or the one you last changed, right? Can I do it by timestamp or something? There are a lot of valid answers here, and actually, we support quite a few of them. And I'm gonna show you sort of how the app. Well, here, let's see if the punchline actually works. I'm gonna turn Wi-Fi on. This actually takes a couple seconds just to connect back up, and hopefully the answer is gonna be level 6 eventually. No, just wait. This one. The maximum timeout, if this doesn't say level 6 within 90 seconds, we know that I probably messed something up. Because that's sort of the max time. We do this exponential back off kind of thing, whatever. Who's keeping track of the time? There we go, all right. Phew. That's the scariest part, yes. Thank you very much. So it went to level 6, and it actually did that because I, as a developer, said that's what I wanted it to do. And so you've sort of outlined kind of the underlying mechanism. Well, you really kind of have different possible answers. Then you have to choose one of these things. The way we've built data stores is with the idea that you actually sort of tell us up front what rule you want us to apply, and then we apply that rule. And so let me jump to the slides again and show you a couple pieces of code, and we'll get to like why this did the thing that we expected it to do. So here's the backup plan, by the way. That's a video. Let's put a pin in sort of the conflict resolution. Let me just show you some basic. This is JavaScript code, so this is for the like HTML version of this. And this is kind of what it looks like. I just want to demystify it. Before we get deep into like how does it work behind the scenes, I just wanted to show you kind of, as a consumer of this is what you do. You call things like get or insert, which is like if a record exists, I'm going to get it. Otherwise, I'm going to insert it with these default values. And then you can get a field, so get level. So that's what's happening here. And we're responding to changes by doing this. We're saying every time anything changes, I'm going to rerun that code that we just saw. So I'm going to go get the latest record and get the latest level. And so that's how these things stayed up to date and sort of in real time we're syncing. Because every time I make a change, this thing would fire on all the other ones and it would update. And so how did we make a change? This is the like click handler for the box. And it just sets the level to the previous level plus 1, right? So that's just doing an increment. So that's that stuff, and then here is why it did the thing that we expected it to do, which was give us the maximum, because I actually told it. What I did is when I sort of created this in my code, I said, for this table, I want this resolution rule, that when you have a conflict on the level field, I want you to just take the maximum. So there are other possibilities. You could have the server wins, or you can have the client wins. You could take the minimum. There's sort of a variety of these things. We supported a few of them. The protocol that we built means that we can support anything, and we can build sort of custom conflict resolution and give what Ray here suggested, which is just give me the options and let my app decide. That's something that's possible. It's something that our SDKs don't currently do, but the actual server protocol basically does that. It gives you that ability. I'll leave the sort of how that works part to Guido, but that flexibility is actually in there. So this is what it looks like in JavaScript. This is what it looks like in Java. This is the Android version. These are the actual lines of code from here. And then this is the version in Objective-C. I just want to show it because like a big part of this is that cross-platform part. So I wanted to show you that it looks pretty similar in all those. So let me show you, just to drive home like sort of where conflict resolution and these custom rules come in. Let me show you another demo. I've built another amazing app. I'm really on a roll with these things. Where's the other one? Okay, we'll do this. So this game is called New High Score. Every time you click, you get a new high score. It's really addictive. At one point today, while I was testing this out, I turned to Greg, who was sitting next to me, and I said, I'm at 300. I've clicked this thing 300 times. So I had this realization that I found it addictive. Okay, let's take this one offline. So we're going to tempt fate again. And the way I think of this, so there are multiple ways you might interpret this, but let's say that this game in real life is like me collecting coins or something, that there's something that I'm collecting over time, right? So far I've collected 10. Now I'm gonna collect 2 more over here, and I'm gonna collect 3 more over here. The reason I'm saying it this way in terms of collect is because I want a different answer here. I don't want, when we go back online, for the answer to be 13 because that was the higher number. I want somehow, I started at 10 and then I did 2 more on one device and 3 more on another device. And so I want the answer to be 15 at the end of this. And it turns out that's something we support also. And so hopefully, another fingers crossed moment, but it worked well last time. There we go. They both go up to 15. Yay, data stores. All right. So there, it was like basically that same line of code before that said like max, instead it said sum. That's it. Like, so it's just a different kind of rule. And that's how we've sort of set up data stores, is that you kind of specify these policies and then we make that happen. So the question you should all be asking now is, all right, well, how does that conflict resolution actually work? Because this is actually a non-trivial thing to implement. And the answer is that I have no idea, but Guido knows all about this. I'm going to turn things over to Guido van Rossum, who is the benevolent dictator for life of the Python programming language, and also we're fortunate to have him here at Dropbox working on the API team, and he's responsible for a lot of the good ideas in data stores and sort of the server protocol and kind of how this whole thing works. So Guido, if you want to come up and we'll plug you in.
Plug me in, Steve.
Okay, I don't like how you said that.
Okay.
This is the hardest problem in computer science, is switching laptops. Now that we've knocked off conflict resolution. Okay, looks good. All right, let's have a round of applause for Guido.
Hello. So I can hear myself just barely. Does this sound good? Okay. Yeah, so how does this work? I have a completely different approach to this. I'm not actually going to show a single line of code. I'm going to do a bit of philosophical talking and thinking about how you should think about the state of your app so that you actually have a chance of writing a successful app using this API. I'm going to talk a bit about what is the nature of conflicts, where do they come from, and how should you think about these conflicts in order to be successful in using the API? Because it's not, I mean, this API is pretty magical, but we can't do it without the application's help. I am going to explain in great detail how we actually resolve conflicts, because teaching that is part of sort of training you to think right about conflicts. And I'm going to end with a few ideas about how to model your data, and then we'll go to questions. So, what is the state of your application? My idea is that the state of your application that we care about here is whatever your users care about. So, what is it that your user wants to see synchronized between their multiple devices, browser tabs, whatever? For example, the level they've unlocked in the game, or how many coins they've collected in the game. If you're writing an ebook reader, probably the last page there are in each particular book, even if they have copies of that book on different devices. Hello, I'm going offline. Yeah, I'm pretending that doesn't happen. If they're using a to-do list application, that's sort of everybody's favorite example. The contents of their to-do list, not the font or some other things. So the long and short of it is that you store it in some kind of database, and that means you have to think about how to model your data so that it actually will go smoothly into that database and come out of it again. And you have to think about your model in such a way that helps with conflict resolution. Oops. So where do the conflicts come from? Well, Steve pretty much showed it in the demo. The conflicts happen when you have two devices that start out in a synchronized state, like everybody agrees that your current high score is 0, Then one of the devices goes offline, or perhaps both devices go offline. Then you make changes on each device that somehow don't yet get synchronized. So the changes start with a common state, but the states diverge. Finally, all the devices come back online. It's sufficient for there to be a conflict for just one device to have gone offline and have made some changes, while the other device was online and still made changes. There's always a server in between in the case of the data store API. Thank you so much. And once both devices can communicate with the server again, that's where you have your conflict. Unless, of course, as a user, you were sort of naive enough to only use one device, or you only use one device at a time. But that's, for a user, it's really hard to keep track of which device they're using. I have like 3 different devices that I use to read the same ebooks. And when I'm reading, I don't even know which device I'm using. I just sort of read the book, because that's the interesting part. So, well, yeah, why are conflicts bad? The user doesn't like their data to get lost. They don't like their data to be modified in ways they don't expect. They really hate losing time having to resolve those conflicts. Like the process that Steve describes, trying to resolve what you changed in one version of the PowerPoint and what you changed in another version of the PowerPoint. And unfortunately, even with Dropbox, both Steve and I and other speakers at Dropbox have experienced that very problem in the last week. It's amazing. And of course, the net result is if your app doesn't do this right, the users won't like you. So I have developed a visual aid for understanding what's going on here. Let's say, very abstract, we have device A, device B, and a server. And Steve's demo actually involved essentially 4 devices, 2 mobile devices and 2 different browser tabs. It's actually sufficient to understand what happens when 2 devices are involved in the problem. So let's start with a very happy state of the world. We have device A connected to the server. It's fully synced up. We have device B also fully synced up. Everybody's talking to each other, and nothing's happening. So now let's suppose on device B, we actually click our button, we actually aim for the right spot on the screen, and the state bumps to 3. What the app is doing at this point is it's sending that change to the server. And the fact that I drew the arrow in green means that in this particular case, the server actually likes that change and accepted it. And now the server also knows that the user's level is 3. Note, however, that device A, while we were working on device B, device A went offline. That's what the dotted line means. Now we pick up device A, which is still offline, and we play a few more rounds of the game. Now on device A, we're at level 4. Okay, we have conflict, but device A is offline, so device A doesn't know that there's a conflict, nor does the server, nor does device B. Next step. Device A comes back online. The first thing it does at that point is it tells the server, hey, I just changed from level 2 to level 4. What do you think of that? And the server says, that's not right. I already received a change from device B telling me they went from level 2 to level 3. And understand that the server has no concept of what kind of game this is. It doesn't even know it's a game, of course. So the server can't just assume that the correct answer is, well, everybody should bump to level 4. And in fact, in the second game that Steve demoed, that wasn't the right answer anyway. So the server, the only thing that the server does is tell the client that was the wrong answer. The next thing that happens is that the client actually asks the server, well, what did you think happened? So now the server tells device A what it had heard from device B. So now device A is fully responsible for resolving this conflict. It knows I changed from 2 to 4. Apparently someone else changed from 2 to 3. Now what am I going to do? And here it's up to the app and to the rules that the app told the SDK, and up to the SDK to decide how to resolve this conflict. I'm going to expand on what actually happens in this box in the rest of the talk, but let's say the outcome is, in fact, that the state ought to be 4. So device A has decided that it wants to go to state 4. It sends that information to the server. The difference is that now it tells the server, I started with the state 3 that you just sent me. The server says, okay, going from 3 to 4 is fine, so it accepts that change. It updates its copy of the state to 4. And the server is the party that takes the responsibility for also broadcasting this to all other devices that have signed up to receive updates for this same data store. So the server, in this case, sends that same information, the change from 3 to 4 to device B. Device B didn't have any local changes because I wasn't playing the game there, so device B is also fine, and everybody's a happy camper again. Let me show a completely different visual aid that also represents the same scenario. So we have a timeline which is the state that the server is happy with. At some point, device A and device B diverged in their timeline, and the purpose of the conflict resolution is to converge again so everybody can continue agreeing on what the timeline is. So this is why we have to resolve conflicts. In the case of the Dropbox Datastore API, by the way, it is always a client that actually resolves the conflict. The server is essentially a passive bookkeeper. All the server does is it takes changes and it says, yes, I've accepted this change, and then it sort of records that change, or it says, no, I don't like that. There's a question.
The second client, is the server telling the client this is the new value, or does the second client have a vote?
The question is, does the second client just hear from the server, or does the second client have a vote in the process? In first approximation, the client does not have a vote. It just hears, this is the new state. If it disagrees with that new state, it could construct a new change and send that back to the server. But you'd sort of, if different clients try to do that with different ideas of what the new state would be, you keep sort of going around in circles. It's a little bit like if you're using Git or Mercurial, if you push your changes and you find that someone else already pushed a change, you have to pull changes and merge or rebase and push again. Well, the worst case scenario is that you'll never converge because someone else is always there before you. In practice, sooner or later, the real life takes over and it converges again. So let's look again at that box with the star. What exactly happened there? The key thing that's important to understand here is that even though we think about the state of the app or the state of a data store as sort of, there's this level, or maybe there is 100 records or 10,000 records containing addresses or whatever. The things that we communicate with the server are actually deltas or changes. So we never send a new copy of the whole state. We always tell the server, this particular small aspect of the state changed. And there's a whole language in the protocol definition that sort of defines how the client and the server can communicate these changes to each other. So in this particular case, the change that the delta that A has says the level changed from 2 to 4. That actually, there's not much of compression there. We don't say we change these bits in the number. But conceptually, it's the same idea. It's a change, not a new. It's not the new state is 4. We change the state from 2 to 4. Now we found out that the server refused that, and the server then sent the client a different delta. It said the state changed from 2 to 3. Now it's the client's responsibility to take those two deltas and come up with a new delta that represents the outcome that the client actually wanted. In this case, the delta that the client has to send to the server to get the desired result is it has to send the server, it changed from 3 to 4. And that is what the server will then accept. So the way conflicts are actually detected by the server are very simple. We just have revision numbers assigned to each state. So the initial state of a data store, there's absolutely no data in there, is always assigned revision number 0. And every time a client sends a change to the server and the server accepts that change, it bumps the revision number by 1. It's always sort of 1, 2, 3. There are no other numbers. It's always contiguous, basically. So whenever a client sends a delta to the server, also whenever the server sends a delta back to a client it's sort of propagating on behalf of another client, the important part of the delta is always the starting state, the starting revision. So the revision is essentially a name for a particular state. Everybody agrees that state 0 is a particular contents of the data store, and after a while, everyone agrees that state 1 is a particular content or snapshot of a data store. So at any point in time, either you know what a particular revision refers to, or you haven't heard of that revision yet, and then you have to build it up by applying deltas from the last snapshot that you do have. There's no ambiguity about what sort of revision 42 refers to. Either you know, and then everybody agrees, or not everybody knows, and the ones that don't know have to sort of find out what it is. So for the server, it's very, very easy to decide whether to accept or reject a change. I mean, first of all, of course, the change has to look right. It has to be a valid change. But then the most important thing is, what is the beginning revision number of the change, the delta that the client sent me? And if that revision number matches the current revision number on the server, it accepts it, and otherwise it rejects it. That's all there is to it. So the client is completely responsible for reacting to that rejection by the server and trying again. And then it better send the server a delta that starts with what the server just told the client is its current revision number. So eventually this converges. So back to that fork in the road diagram. Let's simplify. The essential part, of course, is this little square. I hope I drew it kind of squarish. So let's rotate it 45 degrees, which makes it a little easier to talk about. And let's look at some points of that square in detail. This is the top left corner. Let's say we're at revision 1, and the state is something. Let's say the state is X. So the server received a change from some device that said append Y to X. You know, the server accepted that. Where this change came from is not actually relevant for this part of the resolution. But the server now has revision 2. On the other hand, the client, starting out in revision 1 and the state containing X, the client did something. Suppose the client did something different. It added a Z to the string. So now essentially, well, I didn't manage to draw it quite square on this diagram, but this is sort of, these are the two sides of the square that cause the timeline to fork. The client went to revision 2 containing the state X and Y. Sorry, the server went to revision 2 with state X and Y. The client went to something else, and that revision doesn't actually have a name because the server hasn't accepted it yet. We just hope that it will be revision 2, but unfortunately it's not going to be. So what the client has to do somehow is it has to come up with a different change. And let me see if I can find a cursor here. No, I cannot. Well, yeah, I can't see it on my screen. Okay, well, forget about that mouse pointer, but what we want is we want to tell the server about that green arrow that will take the server state from revision 2 to revision 3. And through the magic of some algorithm, the client actually comes up with something that it sends to the server that has the desired result of merging the states in a fashion that is appropriate to the application. So in the case of Steve's first app, the merging was taking the maximum of 2 integers. In Steve's second app, the merging meant adding 2 numbers together. Or actually, what we do in that case, we convert a change from, it goes from 1 to 3, we convert that in, we add 2. And so the other change that was initially, it goes from 1 to 2, we convert that into, we add 1. And then we combine those two, add 1 and add 2 becomes add 3. And that's the sort of the final state. And assuming that the server didn't receive another update from another client first, the server will actually accept that. The client will find out that the server accepted it, and everybody's happy again. Yeah, sorry. Is there a difference between the client and the server? Absolutely. In the Dropbox sort of world, the Dropbox way of thinking about these things, the server is the authoritative sort of note taker that records the state and that assigns revision numbers. The server is the only party that can assign revision numbers. If you're familiar with the sort of the mathematical theory of operational transformation, there is a variant of the associated algorithms that doesn't assign sort of primacy to any particular party. It turns out that the conflict resolution algorithms become much more complicated, and it's more sort of, it's much more work to obtain a result. We have other requirements for the algorithm, basically that the client application can choose its own fate. It can sort of implement its own way to resolving things, which means that it's much more convenient to say we only talk to the server. The client and the server have to agree. Once the client has convinced the server that a particular new state is reached, the server broadcasts that to all other clients. So it's not a peer-to-peer protocol in particular. One more note about this particular slide. Even though I labeled the arrows as add z, both vertical arrows, which represent sort of client-side changes, are labeled add z, and the horizontal arrows are labeled add y. But it's not actually the same operation. The add z in the first case adds the z after x, in the second case adds the z after y. And, actually, it turns out that the vertical add y and the top add y and the bottom add y in this particular example are the same, but the client operations are different. Anyway, that's a lot of theory, and I'm not going to go into a lot more detail, but I'm going to sort of bring up a few examples from real life where conflicts naturally happen and how you would want them to be resolved. So let's look at text. We'll also look at the to-do list and at an address book. So let's say I'm implementing a text editor. I start with the phrase, I like Dropbox. And on my iPad, I change it into, I really like Dropbox. On the other hand, on my Android phone, I change it to, I love Dropbox. I don't just like it, I love it. So what should happen here? Well, I really love Dropbox. Thanks to Andrew for that example. Now, this particular text editing example is sort of more theoretical example than a practical example, because we don't we don't represent text in this fashion, and we don't resolve it in this fashion, although we could, and one day we will. Let's look at a different example that we can actually implement completely in this, I believe, was the literal text of my very first demo long before we had the actual implementation ready. Suppose I've got a little shopping list. I want to buy beer, I want to buy bread, I want to buy eggs. Well, I have them in a particular order, and somehow the beer was more important than the eggs, but I changed my mind and I figured I should really make sure I have bread and eggs before I consider spending money on beer. On the other hand, another night I thought, actually I like wine much better than beer, so let's change the beer to the wine. So how do we want to merge these conflicts? Well, what I want to happen and what our implementation can actually do for you is that it both reorders them so that the alcoholic beverage comes last, and it changes the nature of the alcoholic beverage from beer to wine. And that's conflict resolution done right. So let's think about yet another type of application, contact list. I have John Doe in my contacts, and on one of my devices, I found out that John Doe changed herself to Jane Doe. Now, independently on my other device, I figured out that John's phone number actually changed because he or she moved. And of course, I need to keep both changes in my contact database. So again, what I want to happen is that both the name and the phone number change, even though they're affecting the same record. If I represented my contact list naively as a text file, those would be two changes to the same line, and your typical Git or Mercurial conflict resolution merge algorithm doesn't do that. However, if you sort of store this properly using a database-ish representation, you can get this right. Another example, if I add Larry Wall and Yukihiro Matsumoto to my contact list, suppose I added them both at the very end. Again, Git and Mercurial are going to ask me, in what order did you want them? Which I don't care. It's a database. It'll sort them by last name, or maybe by first name these days. So I just want both entries to be added. And again, if you model your data correctly, that's what will happen. So the data model that we pretty much force you to use when you're using the Dropbox Datastore API, simplified, is you have to break your data up in records, you have to break your records up in fields, and optionally, a field can actually contain multiple values. For example, you can have a whole bunch of email addresses associated with the same person in your contact list. On the other hand, there are two other concepts that are important for your data modeling, but that aren't really directly involved in the conflict resolution. Of course, there's the notion of a data store. We actually allow you to have multiple data stores to represent different collections of data that are completely unrelated. And sort of, if you have a hard time deciding whether you want to use a single data store for different types of data or whether you want to put your data in different data stores, you have to think about whether the transactionality in your data model. If you want some kind of transactionality, if you want to be able to say, I'm changing this piece of data and I'm changing that piece of data, and now I want to sync again with the server, then you have to put the data in the same data store. If you don't really care about transactionality, you could put them in different data stores. There are other uses for different data stores that will eventually become clear in the future. We also do support tables because tables are useful for modeling your data. But in our implementation, tables are mostly fiction. They're used in the API, but they're not actually part of the conflict resolution algorithm, except that the table ID is sort of silently assumed to be a prefix of the record ID. And you can query by table. So the data types, again, we give you a completely dynamic schema. We don't ask you to start with the create table statement or anything like that. You can just start using the data store in any form you want. You can say, oh, let's create a record and let's put it in a table X and give it some fields. And you can say independently, oh, let's create another record. Maybe put it in the same table, maybe put it in a different table. The important part is that the record is identified by a record ID. And the record is broken up into fields. Fields have field names. A field name is roughly an identifier in your favorite programming language. A field value can either be a list of values or it can be a primitive value or an atomic value like a Boolean or an integer or a float, different kinds of strings or a date. Lists are your typical Python or JavaScript or Java or Objective-C array data type. It's sort of a variable length, and it's a list of objects. So you could have a list that contains a few strings and a few integers and a Boolean. In practice, you almost always have homogeneous lists. But our data type implementation doesn't enforce that. The only thing that it enforces is that you cannot nest lists inside other lists, because that would sort of be just too complicated. So what can you do with records? It's very basic. We have an insert operation, we have an update operation, and we have a delete operation. To talk about records, you identify a record by a record ID, except when you insert, you can leave out the record ID, and then the library will assign a record ID to the record. And the way we auto-assign these record IDs is it's guaranteed to be unique across the entire galaxy. On the other hand, Steve's example, for example, his example code, the record ID was a fixed string, so that's also completely reasonable. Your application can make up fixed strings or can have a number of fixed strings. And in fact, in practice, the fixed strings you can come up with are also always different from all the IDs we can possibly auto-generate. So there are actually two types of insert operations. One that is more like a get or insert, and one that is a guaranteed new insert. The former type can also cause a conflict. Updates can cause conflicts. You say, here's a record identified by this record ID. Go change these fields. Leave the fields that I don't mention unchanged, but go make these changes. And of course, you can delete a record, and then you're not telling exactly what the content is. You're deleting it. You're just deleting it. So these updates, and also actually the collisions that could be caused by inserts with a given record ID. The field level operations for the updates are very simple. You can set a field or you can delete a field. When you set it, there are two different things that can do it. It can either insert a new field if a field by that name didn't exist in that record, or it can replace an existing field, but we use the same operation for that. And this is where almost all the effort of the conflict resolution goes. You can also delete a field, and the only important conflict resolution rule for field deletions is that the delete operation always wins. Finally, if your field value is a list object, we also support a number of list operations. So the list operations, which only apply when your field contains a list value, are insert, where we say at a particular index, insert an extra value into the list, or replace at a particular index the existing value at that point with a different value, or delete whatever exists at a given index, or move the value at index 1 to position 2, index 2. There are pretty complicated rules for resolving conflicts at the list level. I'm not going to give those rules. I'm just going to hint that the right thing will happen. But let's first take a step back and let's sort of consider how we resolve conflicts in general. The basic algorithm for resolving conflicts between two changes, two deltas that came from different sources, is it takes each individual change, it takes the changes pairwise, a change from device A and a change from device B or from the server, and it makes a very simple analysis. If the record IDs differ, then there cannot be a conflict. We never consider a conflict affecting different records. So if it's two inserts for different record IDs, or two deletions for different record IDs, or two updates, field updates for different record IDs, there's no conflict. So everything else below the first bullet is what if it's the same record ID? Well, we have a number of field operations. We consider those one at a time. For different field names, again, we consider there is no conflict. If you change the name on one side and you change the phone number on another side, or you insert an email address on the other side, no conflict. The changes can be cleanly merged, and in particular what that means is it doesn't actually matter in which order you carry out those operations. If I change the name first and then change the phone number, or if I change the phone number first and then change the name, the outcome is exactly the same, so I can just commute those two operations. Another rule is if one of the operations is a record level delete, then whatever other changes were made to that record by the other side are lost, because deletions win. If you don't want deletions to win, you have to implement deletions as some other operation in your application, so you can sort of take over control over deletions. But for normal conflict resolution cases, we thought about this, and it looks that sort of deletion wins is the right approach.
Delete, you say only delete if my revision matches the server revision?
Question was, can you specify to only honor the delete if the revision matches the server revision? We do not currently have that option in our API. A custom conflict resolution algorithm could sort of make that designation, though. Because we have an SDK that has a bunch of canned resolution rules, but we also have an HTTP level API where you can implement your own conflict resolution from scratch if you want to. And eventually we'll give you more control over how the SDK resolves conflicts also. We'll probably just give you a function that gets called if you specify it when there is a conflict at a certain level. We don't currently have that API, but you can do it at the HTTP API level. So at the field level, again, a field deletion wins over a field replacement or insertion. Now, actually, a field insert and a field delete could never be a conflict, because it can't be an insert and a delete at the same time, because what was the initial state? Was the field there or was it not there? But other than that, the deletion wins over the change. And finally, we have, of course, the crucial case. What if I change the phone number on one device in a certain way and I changed it in a different way on a different device? Well, we have a bunch of rules, and that's sort of where Steve's example already showed two of the rules we support. Finally, if a field value is a list of values, a list of atomic values, we have a fairly traditional operational transformation algorithm that we apply. And I hope I have a few things to say about that later. But the basic sort of thing I want you to take home from all this is what is the high-level effect of all these complicated conflict resolution rules? If you model your data right, the automatic conflict resolution will actually do the sensible thing. But you have to model your data right. For example, you shouldn't be modeling your level as a string representing the level as a decimal number, because there's sort of the maximum of 2 strings is undefined. You should model it as an integer. And that's a very simple example of the general rule that you have to sort of choose your data model with conflict resolution in mind. So let's take the contact list example again. The logical way to model your contacts, and this should come as no surprise if you've ever thought about how to write a contact management app, of course, is each contact is represented by 1 record. And in our case, I would strongly recommend using the auto-assigned random unique IDs and not trying to play with automatic deduplication based on the data. I mean, you could do something like take a normalized version of the email address or the full name or something and use that as the record key, but you'll always find that somehow you happen to know 2 Jane Does and they're not the same Jane Doe. Or you have 2 different people who happen to live in the same house and they have the same phone number. I know that was before mobile phones that example made sense. Still applies to me and my wife. So again, you pick your fields so that the field level edits do the right thing. So you put the name in one field and you put the phone number in a different field and you put the email address in yet another field. And altogether, this means that your contact application will behave naturally for the user under almost all conditions. And yes, occasionally there will be one user who does something really weird to their contacts and they're surprised that they end up with duplicate records or that they don't end up with duplicate records, but it's very rare and it's pretty much the best you can do. So I left one thing unspecified, and that is what to do with these fields when there is a conflict. The first rule, actually, the first assumption is that you use fields to store relatively small amounts of data, like a name or a phone number or a level, not your PhD dissertation. That's not an appropriate amount of data to store in a single field. You have to somehow structure that differently. And so what the data store SDK actually does for you is, all it does is it has an algorithm to pick a winner when there are 2 conflicting updates to the same field of the same record. And we actually have 5 different algorithms that we give a name, and you can choose which of those 5 algorithms to use. They're barely worth the name algorithm, of course. The first and default choice is the server wins. The second option is the client wins, if you really didn't like the server wins thing. Then you can use the largest or the smallest value for numeric fields, and for numeric fields you can also treat it as a counter or an accumulator. We actually support adding up floating point numbers as well. In the future, we're thinking about giving you a sort of a hook into this so that you can define your own algorithm, possibly even define your own algorithm that takes the context of the whole record, of the whole change if it affects multiple records. That is still very much sort of a pipe dream. If you wanted that today, you would have to write your own stuff based on the HTTP API. But we have thought about it. So what exactly happens to lists? If there is sorry, was there a question here?
Do you have a conflict resolution based on last change?
Okay, I'm going to have to come clear about this because I think the same question was asked when, and Steve dodged it successfully. I will not try to dodge it. The question is, do you have an option to choose the most recently changed?
And I'm going to ask, what about time zones?
Well, so my answer is we don't even give you that option. The reason is that, and you just mentioned time zones as one particular potential reason, but in general, you can't trust the clock on the device. So if 2 devices have been offline for any considerable number of time, and they both said, I changed it last, there is no way to know whose clock was actually synchronized with the real clock. And there are many different scenarios, and time zones is just one of them, where what the device thinks the time is bears very little relation to what the actual time is, and certainly what two different devices think the time is completely uncorrelated. So we don't even give you that option. If you want to trust your clock, you can store a timestamp and you can try to solve this at the application level or using the HTTP API, but we strongly recommend not actually worrying about that. So I'm sorry, but that's the whole story as it stands at the moment. Conflicts for lists. So the basic idea is we have two list operations like insert something here and move something from here to there. Essentially, we need to transform first this operation, then that operation into first that operation, then this operation in such a way that sort of the intent gets preserved, which means that if you insert something at position 3, but then the other device deletes position 0, the insert should sort of have its index commuted to, say, insert at position 2, because position, let's take this example. Yeah, so in the box, the top two boxes, say we have a list containing the items A, B, and C, and the operation is insert X after the second element. What the user really meant was insert X between B and C. The two boxes on the left have a similar thing where we say insert Y after the third element. And again, what the user really meant was insert Y after C. So, and now, there's a typo. What should it be? Exactly. What I meant to type there was ABXZY. So the insert index for X is actually unaffected in this case, but the insert index for Y gets bumped by 1. Otherwise, Y would suddenly be inserted before C instead of after. And the whole point of a list is that you preserve the order of the items. There are many special cases. For example, if you replace an item and then delete it, well, it turns out that you can just forget about that whatever you replaced it with, because that's being deleted afterwards. If you move something and then replace it, or you replace it and then move it, there's certain rules that apply. If you have a move followed by a delete, again, you can just forget about the move and delete the item at the original position. There's like a whole 4x4 matrix of different cases, and each case has a couple of different subcases based on whether the index in the one operation is before or after the index in the other operation. There's also the interesting case of how do you decide what happens if you have two inserts at the same position? Well, somehow you have to pick a stable answer. But we have a bunch of rules, and they are reliable. And the most important thing of all those rules taken together, and again of all the other conflict resolutions as well, is insertions should never be lost. If the user adds new data, we should not lose that data. The worst thing that can, the sort of worst case scenario is that we don't keep the exact position, but in most cases we will actually keep the data in the right position if that position still exists. I mean, if you insert X between B and C and then you delete both B and C, well, X will end up somewhere. It will actually end up after A. The other very important thing is that the deletion never deletes the wrong item. If I delete the value B that occurred at position 2, after B is moved around a bunch, I want the deletion still to delete B, no matter where that B was. I don't want the deletion to suddenly delete the A that is now at the position where the B was before. So again, the rules sort of all conspire to make sure that deletion never delete the wrong thing. And again, replace is a sort of a special case of deletion because it deletes the old value that was there. And so replace also never overwrites the wrong item. If there really is a true conflict, like you replace something with two different values, we use the server wins rule again. I am way out of time. I want to sort of give people some time to ask questions. I only have a few more slides. So how do you go about modeling your data? Well, in first approximation, try to pretend that you're storing it in some kind of lightweight local database. The important part is that it's a database per user, not a database across all devices and all users, just for this user. And pretend it's like SQLite or something. So think of, you have tables, rows, columns that we call fields, rows we call records. Pick a schema, even though, as I said, the schema is not actually recorded in the data store. You don't have to use a create statement. There's not actual any SQL syntax in the API either. But in your head or on paper, on your whiteboard, start by thinking about what your schema should be. Do I need two tables to hold the phone numbers and the people, or do I store everything in one table? That kind of stuff. What are your columns? How do your records refer to each other? The right answer is usually to use a record ID, which is just a string, and store that as a string field. There is no concern about sort of how to index this data. We have a very simple query language, and everything's queried in memory. If your querying needs go beyond what our querying API supports, just query everything and use a for loop over the data and filter it out the way you want it yourself. It's all in memory. It's not going to be very large. You do have to worry about the overall size of your data. We currently limit you to 10 megabytes per data store. That has something to do with the fact that we keep it in memory. We also limit an individual record to 100 kilobytes for similar reasons. Another important thing with picking your model is sort of map your user's operations, the things that your user does, map them to small amounts of operations on your data. For example, if the user inserts something, don't make your app renumber all the records that come after it, because conflict resolution will not understand what you did with the renumbering, and it will get it wrong. You'll probably end up with missing rows and rows with the same order number. So use a different solution like a list where you move things around in the list if you really have to keep order. So the general rule is, if the user does one thing, turn it into a sort of a small fixed number of operations, not a number of operations to all records that could possibly be affected. Use your list fields for useful things. Use your string fields for foreign keys. If you have large data like images, videos, God knows, Word documents, don't store them in your data store. Store them on the file system. Actually use the Dropbox Sync API, which is the data store's sibling API, and is actually combined in the same SDK. If you download and install your data store API, you have the Sync API as well, and they use the same Dropbox account. They do sync separately though, but use that for storing large blobs. So if it gets anywhere near the record limit of 100K or larger, consider that something for the Sync API. Finally, some reminders, and something that sort of makes the Dropbox data store unique. Every user has their own data store or collection of data stores for your app. We actually let you use multiple data stores. The current release of the API doesn't make that very useful. In the future, we're actually thinking about letting users share data stores, so you could use a data store to represent a shareable document. But the important thing is that the user owns their own data. The user chooses to share it if we eventually implement that sharing stuff. But at the moment, it's the user's data, and the developer does not have to worry about storing that data, but the sort of the other side of that coin is that the developer also doesn't have easy access to that data, except of course when the user is interacting with the app, because you obviously whatever the user types into your application, the application has access to. But once it's sort of stored in the data store and your app has exited, the user has exited the app, or maybe even turned off the device, the data is safe on our server, the data is safely cached on the device. The application developer does not have access to the data. So that's something to think about. And I'm actually going to skip these examples because you've already seen all these. Well, so another category of useful apps was fitness apps, which is actually Leah's favorite type of apps. Yes, to start with the questions.
How do you get back to a particular version?
The question is, can you go back to a previous version of the data store?
Oh, sorry, that's me.
What'd I do?
Sorry, that was me. That's just me.
Miss Fitness app. So using the HTTP API, you can go back to a previous version. Using the SDK, we currently don't give you direct control over those versions. The SDK really sort of presents this fairly convincing fiction that you're sort of putting data into a database and you're getting it out, you're querying it or you're fetching it by record. And every once in a while you say sync, and then we shuffle it to the server in a background thread. But we don't directly let you talk about what did the data look like 3 revisions ago or 3 days ago.
Is a version about a particular field, a record, or a data store?
A version is for a whole data store. So you can actually use this in a sense to implement some kind of transaction-like thingies. I don't really want to call them transactions because of the sort of the conflict resolution, but if in the case where there are no conflicts, if you make several changes and then you bind those changes together by after the last change you say sync, you always have to say sync, by the way, read the documentation for that. What another device will see is either the state before you did the first of those changes or after the sync, but never sort of an intermediate stage where one record was changed but the other was not. So within reason, you can actually have sort of correlating changes in different parts of your data store, as long as it's in the same data store. We don't guarantee anything about ordering of transactions between different, synchronization of different data stores. Okay, you're next.
Okay, apparently we can't do that.
Maybe too close. I can just ask. So the question is, what if the developer wants to do any data mining off of the user data? Like, for example, how many coins have all my users collected in total?
Okay, so the question is, what if the developer really wants to observe a particular statistic or property across all users? So the current approach would be you have to maintain your own server where you call back and you store that. But that will give you partial results because you don't know what happens when the device is offline. And it's also somewhat tricky to sort of keep that information synchronized and up to date as the app sort of goes offline and online. We're also considering a feature where we will let developers export all the data for all their users together. That's a pretty privacy-sensitive operation, so that's a feature you have to explicitly request as a developer before you launch your app to your users, and we will warn the users that the app developer has access to the data. That feature doesn't exist yet. But if you're interested in that, give us a call. Okay?
You said we should use foreign key for too-many relationship, but do you support something like a cascade delete to ensure that there's no dangling foreign keys?
Unfortunately, we don't. That's something you would have to do at the application level.
Okay.
I'll probably get your mic here. Behind you.
Examples or thoughts on how to do sort of replication between a true relational database and a personal data store? Like, the scenario I imagine is you have 1,000 users and each one has their own personal Dropbox full of data, which is really just a query into some database that you're syncing. I mean, it's kind of an obvious enterprise thing. Any email server that does replication, it's a database.
Usually when you say an application is a database, or when an application is mostly a database, it's like sort of your typical Oracle or Microsoft SQL server that stores all data for all applications, for all users, and it's in part up to the application and in part up to the server to enforce access control, so that maybe the accounting application can see information that the phone number lookup corporate database cannot see, even though they're physically stored on the same disk. We don't have anything equivalent to that. We really sort of, the focus of the Dropbox data store is very much on mobile devices. Start sort of with an application that stores state locally only. My example from which Steve's example is actually derived is playing Angry Birds on a large number of different devices and having to sort of go through the same 20 initial levels to get to the level that I'm actually trying to beat. Because the game is the same on every device, but it doesn't synchronize at all. Or the alternative, the other sort of model that we're trying to compete with here is an app that has its own synchronization solution for data sort of between a user's devices, but that doesn't have a good solution for what if the device is offline. If a device is offline, maybe the app will not synchronize at all. It probably doesn't have conflict resolution, because building conflict resolution is really hard. That's sort of the message we're trying to bring here. But those are the types of applications that we primarily think about. Sort of integrating with an enterprise data level database that contains many different bits of information about sort of relevant to different applications is still an open problem. And what you probably would end up doing is write an application that acts as a bridge.
Yeah, I was gonna. Can I
Oh,
can I jump
yeah,
in?
go
Yeah, I
ahead.
just wanted to. So one pattern that's come up with a few developers who I've talked with is, so you mentioned like email as an example. Like suppose you have some centralized email service, but you would like to have email clients that are able to work offline, like on mobile. And so the question is, well, how do you get, so you have some like source of truth on a server, big server somewhere, and then you have users with devices and you need to communicate that truth to them and then have them be able to work offline. And one thing you can do is, I mean, we've actually not talked much today about the fact that there's this underlying HTTP protocol and there's actually a Python library. Amazingly, Guido didn't mention the Python library that he wrote for this the whole time.
Well, you didn't mention it either.
I didn't mention it either. No, but we have a Python library, and it's not terribly difficult to build libraries for other languages, where you can sort of do this from a server-side app. You can do something sensible from there, and so you can imagine having sort of an app, this kind of bridge idea, where you have an app that runs server-side. And as email messages come in, sort of push them into the inbox, that's the data store, right? Push them into that user's sort of data store. And that way you don't have to worry about all the difficulty of the occasionally connected. When the device comes online, it'll pull down changes from the data store. Outgoing changes can kind of be treated the same way, although you have the problem on the other side of having to read everybody's data store to see if there are changes. So I think it's more likely you do it sort of one way, you push things down to mobile, and then the other way you require sort of an API call to sort of send things back or something like that. So that can work, and especially in that one-way model, it's actually it's not very complex at all. The sort of conflicts you might worry about and whatever just don't happen. It's a read-only client, and it's just sort of a really nice, convenient push API with offline caching. And so that's one sort of way to view the data store.
Can I expand on that just a little bit? So I've talked about devices, and I've mostly talked about device A and B. Well, actually, of course, there can be any number of devices. They all synchronize with the same server about the same data store. In addition, it doesn't actually have to be a device. It could actually be an application running on a server that talks using exactly the same protocol to the Dropbox server and actually gets woken up whenever the server has a change for all the devices. The server doesn't know that this is actually another server. It just sort of wakes it up and says, there's a change and here it is. So that's how you would build a bridge between. Okay, how much you are paying?
All right. I think we have time for maybe a couple quick questions.
Hi. You mentioned I always have to call sync. So don't deal with network states, for example. I have an app and I use it offline, and then I change to Angry Birds, and Angry Birds uses all my memory, and the OS kills my app. And so it's offline, so my changes won't be synced, and I won't get changes from the server until I reopen the app, or do you push down?
Currently, I think you have to reopen the app, but we do save everything to the flash drive on the device. So if the app gets kicked out of memory, even if the OS suddenly reboots, after you've called sync, your data is actually safe.
Okay, we'll do one more question really quickly.
Okay, what about pricing? So like limitation, data usage limitation.
Sorry, can you translate?
Great question. Pricing. How much does it cost for developers? How much does it cost for users?
Like, you know, like we use like 10 GB for day, like for account, regular account. Are there any limitation in this case, like, or anything like you can?
It's all free.
No limitation at all?
So there are limits on that. So like the size of a data store can be 10 megabytes
per
maximum. Per user, yeah. It's one data store, so it's for a user.
Nobody's ever filled that up though, have they? Yeah.
I've talked to someone who actually did.
Really?
They had to use multiple data stores so that they could store more than 10 megabytes. But that's more of a limit because of the way that the data store API works, and as Guido mentioned, like we load it into memory, and that's more of a technical limit. Then the storage comes out of a user's Dropbox. So that's the kind of, if you're wondering, well, how do we not go broke by giving away free space? Well, actually, we give lots of free space and haven't gone broke yet. But that's the model, is that the user owns that data, and that comes out of their quota. So like free users have 2 gigabytes of space, which means they can only store 200 full data stores or something before they run out, and they can upgrade to a pro account or whatever. But
Right.
the idea is that you as a developer are never worrying about that, just like you don't worry about, if you use space in a local app on the user's hard drive, if they run out of hard drive space, they have to deal with that, but you as a developer don't have to deal
I think
with
it's
that.
important to note that it's free for developers,
Yeah.
unlike other sorts. Free for developers, unlike sort of similar things that you would use for mobile apps.
We also, the first
Or
5
other
megabytes of this 10 megabyte large data store, we actually just don't count at all. So that doesn't even count against the quota. We do that because we didn't want somebody to be like out of space in their Dropbox because they've stored lots of photos and now they can't install your app. So the first 5 megabytes we just don't even count, just because we just want to make sure that never happens. So effectively, for 99 point whatever percent of data stores, the developer doesn't pay anything and it doesn't use any space for the user. And so it's truly a free
box
thing.
is truly free.
Yeah, click the box is 100% free for everybody.
All right, well, let's give a big round of applause to Guido and to Steve, our speakers today. Fantastic job, you guys. Thank you so much. Thank you guys so much for coming out tonight. I hope you had a really great time. Hope you learned some stuff about data stores and our APIs. If you have any questions about anything you've heard tonight, or about just our APIs in general, or Dropbox, or basically anything, come talk to any of us in these Dropbox t-shirts. Most of us work here. But if you want to get your own Dropbox t-shirt, we actually have some over by the doors as you leave. So you just go back the same way you came, and there will be t-shirts. If you could fill out a survey, that would be very helpful to us as well. We're hoping to do many more of these meetups, and we really want to hear from you, like what kinds of apps you're developing, what you're interested in learning about our APIs, things like, do you want to know about pricing? Do you want to know about conflict resolution? Do you want to know how this would work with a server application and a client application? All of that stuff, just let us know. Don't step on glass on the way out. And we're actually, after this, we're heading over to Trey, the Mexican restaurant over on 2nd and Townsend, if you want to join some people from Dropbox there and sort of keep the conversation going. So thank you so much. Thank you, guys.